Welcome to this quiet space of learning and rest. I am so glad you have decided to join me tonight. In the stillness of this moment, we are going to set aside the concerns of the day and turn our attention to one of the most fascinating, yet often misunderstood, forces in our entire universe: electricity. It is a force that surrounds us at all times, an invisible thread woven into the very fabric of our lives. It hums quietly in the walls of your home. It flows through the devices that connect us to one another, and it even pulses gently behind your eyes as you process these words. We often take it for granted, seeing it only when we flip a light switch or watch a summer storm roll across the horizon. But there is a deep, quiet magic to how it actually works. A story of tiny particles and vast fields that is far more peaceful than you might imagine. If you find that this journey into the gentle side of science helps you find your way toward a restorative sleep, I invite you to softly like this video or subscribe to our channel. It is a kind and quiet way to support this space, and it helps ensure we can continue exploring the wonders of the world together in these quiet hours of the night. But for now, let's focus entirely on your comfort. If you haven't already, I invite you to adjust your pillow. Find that perfect, cool spot where your neck feels fully supported and your shoulders can finally let go of the tension they've been carrying. Take a slow, deep breath in through your nose. Hold it for just a moment, and then let it out with a long, soft sigh. Feel the weight of your body pressing into the mattress, becoming heavy and relaxed. The world outside may be busy, but in here, everything is slowing down. There is no rush. There is only the steady rhythm of your breathing and the calm pursuit of knowledge. To truly understand the nature of electricity, we have to look past the machines it powers. We have to look past the bright sparks and the heavy metal cables we see stretched across the countryside. We are going to leave the macro world of cities and technology behind for a moment and travel somewhere much, much smaller. Imagine we are shrinking down, becoming smaller than a grain of sand, smaller than a speck of dust, until we find ourselves standing on the surface of a simple copper wire. To our human eyes, a wire looks like a solid, silent, stationary cord. But as we move closer, entering the microscopic realm, we see that it is actually a vast, shimmering landscape of atoms vibrating with potential. This is where the energy lives. This is where the invisible becomes real. Let's step inside that hidden world and see what is actually happening beneath the surface, where the true nature of this force begins to reveal itself. As we settle into this microscopic landscape, we begin to see that electricity isn't a physical substance in the way we usually think of things. You cannot catch a handful of electricity and hold it in your palm like a stone or a piece of wood. It isn't a thing that exists on its own. Rather, it is a movement of energy, a specific state of activity within the materials that surround us. It is more of an event than an object, a quiet, synchronized dance of the smallest particles in the universe. You may have heard electricity compared to water flowing through a garden hose or a pipe. It's a helpful way to visualize the basics, the idea of something moving from one end to the other to do work. But as we drift deeper into the true science of the wire, we find that this analogy, while useful, is technically a bit flawed. When you turn on a faucet, You might have to wait a moment for the water to travel from the valve, through the empty hose, and out the nozzle. But a copper wire is never empty. It is not a hollow tube waiting to be filled with electric fluid. Instead, imagine that the hose is already packed tightly from end to end with marbles. The moment you push one marble into the back of the hose, another marble immediately pops out the front. This is a much closer representation of how a wire functions. The wire itself is made of atoms, and those atoms are surrounded by tiny, buzzing particles called electrons. In a material like copper, these electrons aren't strictly tethered to their home atoms. They are free to wander, drifting gently through the metal like a soft mist. A wire is essentially a crowded room where every single person is already standing shoulder to shoulder. There is no empty space. Every inch of the copper lattice is teeming with these billions of tiny electrons, just waiting for a reason to move in the same direction. When you flip a switch, you aren't sending new electrons into the wire from some distant reservoir. You are simply providing the push that tells the electrons already inside the wire to start shifting. It is a beautiful, constant state of readiness. Even when your bedside lamp is off, the wire leading to it is full of potential, a silent highway of particles held in a delicate balance. They are there, resting, part of the very fabric of the metal itself. Electricity is the moment that rest turns into motion. It is the collective breath of a billion tiny points of light, all deciding to step forward at once. As you lie there, perfectly still, try to visualize this hidden fullness. The world is not made of empty spaces. It is made of structures that are already brimming with energy, just waiting for the right moment to share it. But what exactly does that movement look like? We often imagine these electrons racing through the wire at impossible speeds, zigzagging like tiny bolts of lightning through the copper. The reality, however, is much more rhythmic, much slower, and perhaps even more fascinating than a simple race. To understand the true pace of this energy, we have to look closer at what these individual electrons are actually doing when the current begins to hum. When we think of electricity, we often imagine it as a frantic, high-speed race. We picture tiny, glowing sparks zipping through the copper at the speed of light, rushing from the wall outlet to our devices in the blink of an eye. It feels fast because our world is fast. The moment we touch a screen or flip a toggle, the result is instantaneous. But the reality of what is happening inside that wire is far more patient, far more rhythmic, and surprisingly slow. If you could shrink down and watch a single electron inside a typical household wire, you might be shocked by its pace. It doesn't sprint. In fact, it barely crawls. Scientists call this drift velocity, and for a standard current, an electron moves at about the speed of a garden snail, roughly 1 meter per hour. If an electron started at your light switch, it might take all night just to reach the bulb a few feet away. It is a gentle, stuttering drift, a microscopic wandering through the dense forest of copper atoms. This creates a beautiful tension in our understanding of the world. If these tiny carriers of energy are moving so slowly, why does the light turn on the very microsecond you flip the switch? Why don't we have to wait minutes or even hours for the flow to reach our lamps? The answer lies in the difference between the particles and the signal. To understand this, return to that image of the hose packed tightly with marbles. While each individual marble might only move a fraction of an inch, The push you give the first marble travels to the last one almost instantly. This is because the marbles are already touching. The force is transferred from one to the next in a seamless chain reaction. In a wire, this push is an electromagnetic field. The moment the circuit is completed, a silent, invisible wave of energy ripples through the wire at nearly the speed of light. It is not waiting for a specific electron to travel the length of the cord. Instead, it is a command that reaches every electron in the wire simultaneously. It tells all of them, from the switch to the bulb, to start their slow, rhythmic crawl at exactly the same moment. The energy isn't the electron itself. The energy is the signal that coordinates their dance. It is a shimmering pulse of information that tells the universe to wake up. As you rest, imagine this invisible field expanding through the walls of your room, a silent, lightning-fast ghost that moves with incredible grace, while the tiny particles it commands take their slow, deliberate steps. This distinction between the slow movement of matter and the near-instantaneous movement of energy is one of the most calming realizations in physics. It reminds us that power doesn't always require frantic speed. It requires connection. Because the wire is already full, because the path is already laid, the energy can be everywhere at once. But this brings us to another question, one that touches on the objects we hold in our hands every day. We know how electricity moves when it is invited to flow through a wire, but how do we keep that push ready for when we need it? How do we take this vast, invisible force and tuck it away into a small, quiet space where it can wait for us in the dark? To understand that, we have to look at the humble battery, not as a tank of liquid energy, but as a silent reservoir of chemical potential, waiting for the moment we ask it to breathe. Think for a moment about the batteries in your remote, the one tucked inside your watch, or the thin, flat one resting quietly within your phone. It is very common to imagine these small objects as tiny tanks or buckets, filled to the brim with a liquid called electricity. We often speak of charging them as if we are filling a reservoir, and we say they are drained when they no longer work. But in the quiet reality of physics, a battery isn't a container for electricity at all. Electricity, as we have seen, is the movement of energy, and energy is difficult to bottle up. Instead, a battery is a clever, silent house for a chemical reaction. Inside that metal casing, there isn't a pool of electrons waiting to be poured out. Instead, there are two different materials, often metals or specialized pastes, separated by a thin, protective barrier. These two materials are chemically mismatched. One of them has a surplus of energy it wants to give away, and the other is very hungry to receive it. While the battery sits on a shelf or rests in your device while it's turned off, these two materials are held in a state of perfect, expectant tension. They want to interact, but they have no path to reach one another. This wanting, this invisible tension, is what we call voltage. You can think of voltage as electrical pressure. It isn't the flow itself, but the push that makes the flow possible. It is like a spring that has been compressed and held in place, or like the air inside a balloon, pushing against the rubber, waiting for a tiny opening to escape. The moment you flip a switch or press a button, you are providing that opening. You are completing a bridge or a circuit that allows the chemical reaction inside the battery to finally begin. Only then, in that very instant, is the electricity created. The chemical reaction starts pumping electrons out of one side of the battery, through your device, and back into the other side. The battery isn't giving you something it was holding. It is working to create the flow you asked for. When we say a battery is dead, it isn't because it is empty of a fluid. It is simply because the chemicals inside have reached a state of balance. They have finished their reaction, the tension has faded, and there is no more push left to move the electrons. The spring has fully uncoiled. The conversation between the two materials has come to a peaceful end. This steady, guided movement of energy through a circuit is what we call current. It is a disciplined, predictable flow that follows the paths we build for it. It is the electricity of our modern world, reliable, constant, and controlled. But electricity does not always wait for a copper wire or chemical reaction to tell it where to go. Sometimes it gathers in the silence of the air or on the surface of a fabric, building up its own invisible pressure without a clear path to follow. To understand the true nature of this force, we must look at the moments when electricity isn't flowing in a stream, but waiting in a pool. The mysterious and often surprising world of static. There is a common misconception that static electricity is a different kind of energy than the electricity that powers your lamp or charges your phone. We give it a different name, which makes it feel separate, but in truth, it is the exact same stuff. It is the same restless electrons, the same fundamental force of nature. The only difference is in the movement. While the electricity in your walls is like a flowing river, guided by the banks of a copper wire, static electricity is like a quiet, still pond. It is electricity that has gathered in one place and is simply waiting for a way to move. Static electricity is, at its heart, a story of an imbalance. In the natural world, most things prefer to be in a state of balance, a perfect equilibrium where the positive and negative charges are equal. But electrons are easily swayed. When two materials rub against each other, like your socks against a carpet or a balloon against a sleeve, electrons are physically knocked loose from one surface and cling to the other. One object ends up with too many electrons, and the other with too few. This creates a state of tension. The object with the extra electrons is searching for a way to give them back, to return to that peaceful state of balance. Because the air around us is generally a poor conductor, those electrons have nowhere to go. They sit on the surface, building up a silent, invisible pressure. They are waiting for a path, any path, that will allow them to jump. This is why, when you reach for a metal doorknob, you feel that sudden, tiny pop. For a fraction of a second, your finger and the metal created a bridge, and the gathered electrons rushed across it all at once to find their balance. As you rest now, take a moment to imagine the soft, dry air of a quiet winter evening. Think of the familiar, gentle crackle of a favorite wool sweater as you pull it on, or the way a soft fleece blanket might cling ever so slightly to your skin. In the stillness of a darkened room, these tiny sparks are not jarring. They are rhythmic and small, like the faint sound of rain on a distant roof. It is a harmless, miniature display of physics happening right in your hands. It is a reminder that even in the most mundane objects, the threads of your pillowcase, the fibers of your pajamas, there is a vast, invisible world of energy constantly seeking harmony. For centuries, these little sparks and the strange way that amber or silk could pull at a person's hair were seen as curiosities, little more than parlor tricks of the natural world. People observed the effects, but they didn't yet understand the underlying rules. They didn't see the connection between the spark on a fingertip and the great booming flashes that lit up the summer sky. It was a mystery of scale. To the early observers, the small crackle in a room seemed entirely unrelated to the terrifying power of a storm. It would take a curious mind and a series of patient, thoughtful experiments to finally realize that the small and the large were one and the same. We began to wonder, if a spark could jump from a finger to a door, could it also jump from the heavens to the earth? This curiosity would eventually lead to one of the most famous and perhaps most misunderstood stories in the history of science. When we think of the moment humanity first truly grasped the power of the storm, one image usually comes to mind. A lone man standing in a field during a thunderstorm, holding a kite string with a metal key dangling from it. We are often told the story of how Benjamin Franklin discovered electricity on that gray afternoon in 1752. But, as with many legends passed down through the years, the truth is a bit more nuanced, and perhaps even more fascinating in its quiet details. Electricity was not a new concept to Franklin. By the time he stepped out into that Philadelphia field, scientists and curious minds had been experimenting with what they called electrical fire for decades. They had glass globes that spun to create friction, and they could store those tiny charges in glass jars lined with metal foil. They knew electricity could jump, crackle, and glow in a dark room. What they didn't know, what Franklin suspected with a brilliant intuition, was that the terrifying, earth-shaking bolts of lightning were exactly the same thing as the tiny sparks from a wool rug, just scaled up to a gargantuan size. There is a common misconception that Franklin's kite was struck by a direct bolt of lightning. In reality, if a bolt of lightning, which carries millions of volts and immense heat, had actually struck his kite, Franklin likely would not have survived to tell the tale. He was a careful observer, not a thrill-seeker. He wasn't looking for a cataclysmic strike. He was looking for something much more subtle. He was looking for the electrical charge to seep out of the heavy ionized air and onto his equipment. Imagine the scene as if you were there, standing in the shelter of a small shed to stay dry. The sky is a deep, bruised purple, and the air smells of damp earth and ozone. Franklin used a silk handkerchief stretched over a cedar frame for his kite. A long hemp string trailed down from the kite, and at the end, near his hand, hung a simple metal key. He stayed inside the shed because the silk string near his hand needed to remain dry. Dry silk is an insulator, meaning it doesn't allow electricity to pass through easily, providing him a safe handle. But the rest of the hemp string, reaching up toward the clouds, became wet from the rain, turning it into a conductor. He didn't see a blinding flash. Instead, as the storm clouds drifted overhead, he noticed the little loose threads of the hemp string beginning to stand on end, reaching out toward his hand as if they were alive. It was the same silent tension you feel when a balloon is held near your arm. When he moved his knuckle toward the key, a tiny, familiar spark jumped to his skin. It was the same spark he had seen 1,000 times in his laboratory. In that quiet, rainy moment, he had bridged the gap between the terrestrial and the celestial. He had proven that lightning wasn't a different, mysterious substance or a divine force, but a natural phenomenon governed by the same laws of physics as a spark in a workshop. This realization changed the world, leading him to invent the lightning rod to protect homes from fire. Yet, even with this discovery, lightning remains shrouded in myths. We often imagine it as a single, solid spear of light thrown down from the clouds. But the reality of how a lightning bolt actually forms and moves is far more complex, involving a journey that starts in places we might not expect. When we look at the sky during a summer storm, we see a jagged line of white light that appears to strike the earth from above. It looks instantaneous, like a spear of fire thrown from the heavens. But the reality of a lightning strike is much more of a partnership, a delicate, high-tension dance between the sky and the ground. One of the most surprising facts about lightning is that it doesn't just travel from the sky down. It also travels from the ground up. To understand this, we have to look at what is happening just milliseconds before the flash. High up in the belly of a storm cloud, a massive buildup of negative charge begins to reach out toward the Earth. It doesn't move in one smooth, continuous motion. Instead, it moves in jagged, invisible increments called stepped leaders. Think of these as scouts searching for the easiest path through the resistance of the air. They branch out like the roots of a tree or the veins in a leaf, feeling their way through the atmosphere, stretching closer and closer to the Earth in a series of rapid, invisible jumps. As these invisible leaders descend, the ground below begins to react with equal intensity. The massive negative charge in the sky pushes away the negative charges on the surface of the Earth, leaving the ground, and everything on it, strongly positive. This positive charge begins to pool and concentrate at the highest points, the tips of blades of grass, the tops of fence posts, or the peaks of roofs. In response to the descending leaders, these positive charges start to reach upward in thin, faint tendrils called upward streamers. For a brief, silent moment, the air is filled with these invisible reachings. Then, one of the descending leaders and one of the upward streamers find each other. They connect, creating a complete bridge of ionized air, a perfect path of least resistance. The moment that connection is made, the circuit is closed, and a massive surge of current rushes from the ground back up to the cloud. This is the return stroke, and it is the part we actually see. Though it happens so fast, our eyes perceive it as a downward strike, the brightest, most powerful part of a lightning bolt is actually moving from the ground toward the sky. It is a beautiful, violent restoration of balance. Take a slow, deep breath and imagine that flash of light not as a chaotic explosion, but as this perfectly balanced exchange of energy. If you listen closely, you might imagine the distant, muffled roll of thunder, a sound so far away that it feels like a gentle vibration rather than a noise. You are tucked away, warm and shielded, perhaps watching the soft, diffused glow of lightning behind a heavy curtain of clouds. From this distance, the immense power of the atmosphere is just a quiet light show, a reminder of the incredible forces that surround us, always seeking a way to come back into equilibrium. As we watch these forces find their path, we might wonder why certain things are chosen as that bridge between earth and sky. We often hear stories about what protects us during a storm, why we stay inside, why we avoid tall trees, and the curious reasons why some materials seem to act as a shield, while others act as an invitation. There is a deeply held belief, for instance, that the rubber on our shoes or the tires on our car are what keep us safe from these massive discharges of energy. But as with the direction of the bolt itself, the truth about how materials interact with electricity is often quite different from the myths we have lived with for generations. You might have heard, perhaps as a child or from a well-meaning friend, that if you are ever caught in a car during a fierce thunderstorm, you are safe because of the rubber tires. It is a comforting thought, the idea that those thick black circles of rubber act as a barrier, insulating you from the immense power of a lightning strike. But when we look at the physics of a storm, we find that the truth is much more fascinating and much more protective than a few inches of rubber. If you consider that a bolt of lightning has just traveled through miles of empty air, which is actually a very good insulator, it becomes clear that a small strip of rubber wouldn't be much of a challenge for that level of energy. If electricity can bridge the vast, silent gap between a cloud and the earth, it can easily hop over a tire to find its way home. The true hero of this story isn't the rubber at all. It is the metal frame of the car itself. In the world of science, we call this a Faraday cage, named after the 19th century scientist Michael Faraday. Imagine the lightning as a sudden, massive wave of energy hitting the roof of your vehicle. Because the car is made of a highly conductive material, like steel or aluminum, the electricity doesn't want to go through the air inside the car where you are sitting. Instead, the electrons prefer the easy, wide-open highway of the metal skin. As the strike hits, the electrical charges instantly spread out across the outer surface of the metal. They race around the exterior of the car, following the curves of the doors and the frame, staying strictly on the outside. It is a beautiful display of physics. The electrical field inside a hollow conductor, like your car's cabin, remains at zero. You are sitting in a pocket of perfect electrical stillness, even as thousands of amps of current flow just inches away from your shoulder. The energy simply flows around you, like water rushing around a smooth stone in a stream, before leaping from the metal rims or the wet tires into the earth. This happens because electricity is, in its own way, very efficient, perhaps even a bit lazy. It always seeks the path of least resistance. It is constantly looking for the easiest, most effortless way to move from one point to another. In that moment of a strike, your body and the air inside the car offer a lot of resistance, while the metal frame offers almost none. The electricity chooses the easy path every time. Take a slow, quiet breath and think of that path now, not as a violent event, but as a search for rest. The energy isn't trying to cause chaos. It is simply trying to find its way to a place where it can be absorbed and neutralized. As you lie there, feel the weight of your own body, completely still and supported by your bed. You are very much like that person inside the car, safe, shielded, and tucked away in a place of calm while the great forces of nature move around you in their own complex, invisible patterns. Everything in the electrical world is ultimately trying to reach a state of balance, and for our planet, that balance is found in the dirt and stone beneath us. This destination we call the ground is more than just a safety feature in your home or a destination for a lightning bolt. In the quiet language of physics, ground is a beautiful and mysterious concept. It is the ultimate anchor, the great reservoir of the world, and the place where all energy can finally become quiet and still. When we speak of grounding, we are describing a fundamental relationship between our technology and the planet itself. In the world of physics, the Earth is considered to have an electrical potential of zero. It is the steady, unmoving baseline against which all other voltages are measured. Just as we use sea level to determine the height of a mountain or the depth of a valley, we use the Earth as the universal sea level for electricity. This works because the Earth is unimaginably large. It acts as a massive, nearly infinite reservoir of electrons. Because it is so vast, it can absorb an enormous surge of energy, like a lightning strike, without its overall electrical state changing in any meaningful way. It is like pouring a single bucket of water into the vast, dark expanse of the midnight ocean. The ocean simply accepts it, and the surface remains as calm and level as it was before. But the Earth doesn't just take energy away, it can also provide it. If a circuit needs more electrons to reach a state of balance, the Earth can offer them up from its deep, hidden stores. It is a source and a sink, a silent partner in every electrical system we have ever built. When you look at a three-pronged plug on an appliance, that third round pin is the grounding pin. It is a direct physical connection to the soil outside your home. It is there as a silent guardian, a dedicated path that says to any stray electricity, if you lose your way, come here. Come back to the Earth where it is safe. In many ways, the Earth is the ultimate stabilizer. Without this connection, electrical charges could build up in unpredictable ways, creating static or floating voltages that could be dangerous or simply chaotic. By tethering our wires to the ground, we invite the planet's own immense stability into our homes. We are literally anchoring our lights, our computers, and our heaters to the very bedrock of the world. Take a moment now to feel that sense of being anchored. Even if you are on the second or third floor of a building, or higher still, there is a direct, unbroken line of physical and electrical connection from the space around you down into the cool, dark Earth. Imagine the layers beneath your bed, the soft fabric of your mattress, the sturdy frame, the floorboards, the heavy concrete of the foundation, and finally, the ancient soil and stone. The Earth is steady. It is patient. It is large enough to hold all the energy we could ever produce and still remain quiet. As you breathe out, imagine any tension in your own body simply draining away, just like a stray charge moving toward the ground. Let it go into the floor, into the foundation, and into the deep, welcoming earth below. You are part of this giant, balanced system. And this balance isn't just something that happens outside of us. While we think of the Earth as the great electrical reservoir of the world, we often forget that we carry our own intricate electrical systems within us. The same forces that govern the lightning and the grounding wire are also at work inside the quiet chambers of your own heart and the delicate pathways of your mind. We are not just observers of electricity. We are, in every heartbeat and every thought, a living part of its story. The currents of the world don't just stop at our skin. They begin deep within our very cells. If you listen closely to the silence of your room, you might become aware of the gentle rhythm of your own breathing, and perhaps, if the world is quiet enough, the faint, steady pulse of your heart. It is easy to think of the heart as a simple muscle, a mechanical pump that works tirelessly throughout our lives. But that pump has a conductor, a silent leader that tells it exactly when to move. This conductor is a tiny cluster of specialized cells called the sinoatrial node, your body's own natural pacemaker. Every single beat of your heart begins with a soft, microscopic spark of electricity. This signal isn't coming from an outside source.
Your body generates it itself. It's a rhythmic pulse that travels through the heart's chambers, coordinating the muscles in a perfect, life-sustaining dance.
This internal current is what doctors measure when they perform an electrocardiogram. Those jagged lines on the screen are simply the visual echoes of the electricity flowing through you. It is a very small amount of energy, just a fraction of what it takes to light a tiny bulb, but it is the most important energy in your world. Without this bioelectricity, the heart would not know how to rhythmically contract, and the life-giving blood would not flow. It is a constant, quiet hum that has been with you since before you were born, an internal clock that never stops, ensuring that every part of you receives what it needs. But your heart is not the only part of you that runs on these invisible signals. As you lie there, your brain is a vast and intricate landscape of electrical activity. Every thought you have, every dream that begins to form as you drift towards sleep, and every sensation of the soft blankets against your skin is processed through electricity.
Your nervous system is like a complex network of biological wires. But instead of copper, it uses long, slender cells called neurons. When one neuron wants to talk to another, it sends a tiny pulse of electricity along its length. Think of it as a great silent conversation happening within you at all times. Billions of these pulses are moving through your brain every second, even now as your mind begins to slow down. This isn't the high-voltage electricity of a power line. It is a gentle, liquid kind of energy. It works through the movement of ions, tiny charged particles like sodium and potassium, flowing in and out of your cells through microscopic gates. It is a chemistry of light and movement, a delicate balance that allows you to see, to feel, and to exist. You are, in a very real and physical sense, an electrical being. You are a living system of currents and fields, perfectly contained and quietly humming. When you move your hand, you are sending an electrical command from your brain to your muscles.
When you close your eyes and visualize a peaceful forest, your brain is lighting up with electrical patterns that represent that image. You are a symphony of bioelectricity, a masterpiece of natural engineering that uses the same fundamental forces that power the stars and the storms. As you relax further, imagine these internal signals beginning to soften. The rapid-fire pulses of the day, the stress, the planning, the busy thoughts, are giving way to the long, slow waves of rest. Your brain's electrical frequency is shifting, moving from the busy waves of wakefulness into the calm, rolling waves of deep relaxation. It is like a city at night, where the bright, flickering lights of the center are being turned off one by one, leaving only the soft, steady glow of the street lamps and the quiet hum of the essential systems. This incredible ability to harness electricity isn't unique to humans.
It is one of nature's most ancient and versatile tools. All living creatures have some level of electrical activity within them, as it is the very language of the nervous system. But while we use our electricity to think and to move, some inhabitants of the natural world have taken this force and evolved it into something truly extraordinary. Just as we have learned to ground our homes and wire our cities, certain creatures in the deep, dark waters of the world have learned to use their own bodies as living batteries, turning the quiet hum of life into a powerful tool for survival and navigation. Among these creatures, the most famous is perhaps the electric eel. But science reveals a quiet surprise about this mysterious traveler of the Amazon and Orinoco rivers. Despite its name and its long, serpentine body,
the electric eel is not actually an eel at all. It is a member of the gymnotiform order, commonly known as knife fish.
They are more closely related to catfish and carp than to the true eels of the ocean. It is a master of adaptation, living in waters that are often dark, murky, and thick with sediment, where traditional vision is of little use. To navigate and survive in this dim world, the knife fish has developed a biological marvel within its own body. Roughly 4/5 of its length is dedicated to 3 specialized organs that function like living batteries. These organs are filled with thousands of unique cells called electrocytes. If you were to look at them closely, you would see they are stacked neatly in rows, much like the cells in a modern battery. Individually, each electrocyte produces only a tiny fraction of a volt. But when the fish senses a need, it sends a signal through its nervous system that tells all those thousands of cells to discharge at the exact same moment. This synchronized pulse creates a surge of energy that is truly remarkable. There is a common misconception that these fish only use their electricity as a weapon, a sudden flash of power to catch a meal or ward off a threat. While they can certainly do that, producing a charge of several hundred volts, most of their electrical life is much quieter. They spend much of their time emitting low-voltage pulses, creating a soft electrical field that surrounds their entire body. This field acts as a second set of eyes, a process known as electrolocation. As the fish swims through the dark water, any object nearby, a rock, a plant, or another creature, distorts that field. By sensing these tiny changes in the electrical flow around them, the knife fish can see the shape and distance of its surroundings without a single ray of light. It is a constant, gentle conversation between the fish and the water, a way of feeling the world through the movement of electrons. This natural mastery of current is a reminder that electricity has been a part of the Earth's story long before humans ever learned to flip a switch. It is a fundamental force of nature that we eventually sought to capture and tame for our own needs. As we transitioned from understanding the bioelectricity of the animal kingdom to building the great grids of the modern world, we entered a period of history defined by brilliant minds and intense competition. We often think of the history of electricity as a single moment of invention, a sudden spark of genius that changed everything. But the path to lighting our homes was much more complex, filled with quiet improvements and a famous struggle over how this invisible power should actually move through our world. It was a time of great ambition, where the very way we live today was being decided in laboratories and city streets, leading us into what would become known as the War of Currents. The story of how we brought light into our homes is often told as a series of sudden, brilliant breakthroughs by a few famous men. We like the idea of a single spark of genius changing the world overnight. But history, much like science, is usually a slow, steady process of building one idea upon another. Perhaps the most famous name associated with this era is Thomas Edison. We are often taught that he invented the light bulb in 1879, but the reality is more like a long, patient relay race where Edison ran the final, most successful lap. Long before Edison's laboratory in Menlo Park was even built, other scientists were already experimenting with the idea of using electricity to create light. As far back as 1802, Humphrey Davy showed that passing a current through a thin strip of platinum could make it glow. It was a beautiful, fleeting moment of light, but it wasn't practical. The metal would burn out almost instantly. or it was simply too expensive to be used by anyone but the very wealthy. Over the next 70 years, more than 20 different inventors across the globe developed their own versions of an incandescent lamp. Some of these early bulbs worked quite well. Joseph Swan, an English chemist, had even developed a working light bulb using carbonized paper filaments around the same time as Edison. The challenge wasn't just making a light that would turn on. The challenge was making one that would stay on for a long time and could be produced cheaply enough for everyone to use. This is where Edison's true contribution lies. He didn't invent the concept of the light bulb, he perfected the recipe. Imagine the thousands of experiments his team performed, testing every material they could find, from fishing line to coconut hair, searching for a filament that wouldn't disintegrate. They eventually found success with a carbonized bamboo thread. Combined with a much stronger vacuum inside the glass bulb to keep the oxygen out, this new design could burn for over 1,200 hours. It was a quiet, steady glow that finally made the dream of electric light a reality for the average person. But as these bulbs began to appear in shops and homes, a new problem arose. A light bulb is only useful if you have a way to get electricity to it. At the time, Edison was a firm believer in direct current, or DC. In a DC system, the electrons flow steadily in one single direction, like a peaceful stream. It was simple, and it worked well for small areas, but it had a major limitation. Direct current couldn't travel very far without losing its strength. This meant that if you wanted to use Edison's DC power, you had to live within a mile or so of the power station. This limitation set the stage for one of the most famous rivalries in the history of science. As cities grew and the demand for power increased, a different way of moving energy began to gain traction: alternating current, or AC. Unlike the steady stream of DC, AC pulses back and forth, changing direction many times every second. This difference might seem small, but it changed everything about how we could distribute power across vast distances. It was the beginning of a great debate, a period of intense competition that would determine the very shape of the modern world. This was the start of what would be called the War of Currents, a struggle not just between two different technologies, but between two different visions for how our society should be powered. The world was about to choose the path it would take into the future, and the choice would be far more complicated than a simple disagreement over wires. When we look back at this era of history, we often see a story of two titans locked in a personal battle: Thomas Edison and Nikola Tesla.
Popular culture sometimes paints them as bitter enemies in a cinematic way, with Edison cast as the ruthless businessman and Tesla as the visionary, misunderstood genius. It is a compelling narrative, one that feels like a drama unfolding under the flickering lights of a new age. But the reality was much more grounded in the quiet world of engineering and the practicalities of corporate competition. While they certainly had different philosophies, their war was largely a struggle between two different business models and two different sets of patents. Tesla did work for Edison for a short time, but their paths diverged naturally as their interests shifted. The real competition was between Edison's General Electric and the Westinghouse Electric Company, led by George Westinghouse, who had purchased Tesla's patents for the alternating current motor and delivery system. It wasn't so much a blood feud as it was a series of technical demonstrations, marketing campaigns, and legal filings. GDK aimed at deciding how the world's growing cities would be powered.
Take a moment to imagine those early cities, the street gay beginning to hum with a new kind of life. The debate wasn't just about which inventor was more brilliant. It was about which system was more practical for a world that was expanding. Edison's direct current was safe and simple, but GDK was limited by distance. To use GDK, you had to be very close GDK contrast. Alternating current, or AC, offered a way to bridge the GDK who needed them. The reason AC GDK emerged as the victor for our modern electrical grid comes down to a single, elegant piece of technology: the transformer. Because alternating current reverses its direction many times every second, it allows us to use electromagnetic induction to change the voltage of the electricity. We can step up the voltage to incredibly high levels for its journey across the countryside, and then step it down to a safe level once it reaches your home. In the late 1800s, this was the breakthrough that changed everything. By increasing the voltage, engineers found they could send electricity across hundreds of miles of wire with very little energy being lost along the way. This meant that a single power station, perhaps located near a powerful waterfall or a coal mine far from the city, could provide light and warmth to thousands of homes across a vast region. Without this ability to transform the voltage, our landscape would look very different today, dotted with thousands of small, local power stations every few blocks. As you rest, perhaps you can visualize those long, silver wires that stretch across the horizon, carrying the silent pulse of the grid. It is a system built on the ability to manage the push of electricity. But this brings up a curious question that often confuses us when we think about power. Why do we need such high voltage in the first place? Why does it matter if the electricity is pushed with more force? To understand why the world chose AC, we have to look closer at what's actually happening inside those wires as they travel through the quiet, open spaces of the world. We have to understand the difference between how fast the energy moves and how much pressure is behind it. When we hear the term high voltage, it is easy to imagine electricity racing through the wires at a frantic, dangerous speed. We often associate high numbers with high velocity, as if the electrons were suddenly accelerating into a sprint. But in the quiet world of physics, high voltage does not actually mean the electricity is moving faster. Instead, you might think of voltage as pressure. Imagine a garden hose. If you turn the tap just a little, the water trickles out with very little force. If you turn it all the way, the water pushes against the sides of the hose with much more intensity. The water molecules themselves are not necessarily moving at a different fundamental speed, but they are under more pressure to move forward. In a power line, high voltage is that same kind of electrical pressure. It is the push behind the energy, urging it to do its work. The reason we use this intense pressure for long-distance travel is actually quite practical and surprisingly gentle. When electricity flows through a wire, it encounters a small amount of resistance from the metal itself. This resistance creates heat, a phenomenon known as Joule heating. If we tried to send a massive amount of current, the actual volume of moving charge, at low pressure, the wires would get incredibly hot. They would glow and waste a huge portion of that energy as warmth escaping into the air before it ever reached your bedside lamp. By stepping up the voltage to hundreds of thousands of volts, we can send the same amount of power using very little current. Because there is a smaller volume of charge moving through the metal at any one time, the wire stays cool. It is an elegant solution that allows energy to travel for hundreds of miles with very little waste. It is the difference between trying to push a huge, crowded group of people through a narrow hallway all at once versus having one very strong person carry a heavy load through that same space. The work gets done, but the hallway remains clear and calm. Take a slow, deep breath now, feeling the weight of your body against the mattress. Imagine you are standing in a vast, quiet field at night. The moon is full and silver, casting soft shadows across the tall grass. Above you, the tall, skeletal silhouettes of transmission towers march toward the distant horizon, linked by long, sweeping curves of wire. You might hear a very faint, low-frequency hum, a gentle bzzz that sounds like a hive of bees in the distance. This is the sound of the air molecules reacting to that immense electrical pressure. These lines are the silent arteries of our world, carrying the lifeblood of our modern lives across the sleeping countryside. They are high above the ground, tucked away from the bustle of the day, working steadily while we rest. It is a peaceful thought, knowing that even in the darkest hours, this invisible system is balancing itself to keep our world ready for the morning. And as you look up at those silver threads stretched against the stars, you might notice something else. Small, dark shapes perched perfectly still along the wires. Birds. They sit there quite peacefully, often huddled together in the cold, seemingly indifferent to the thousands of volts coursing just an inch beneath their feet. If that wire carries enough energy to power a whole neighborhood, why is the bird perfectly safe? Why doesn't that immense pressure seek a path through its tiny heart? It seems like a miracle of nature. But like everything in this quiet world of science, it follows a very specific set of rules. Rules that remind us that electricity is not just about what is there, but about where it is trying to go. To understand why the bird is safe, we have to look at the concept of potential and how electricity chooses its path through the world. The bird sits there, its tiny feathers ruffled by a light breeze, its heart beating in a steady, rhythmic pulse. To us, looking up from the ground, it seems like a miracle of survival. But to the laws of physics, it is a simple matter of equilibrium. You see, electricity is always looking for a way to move from a place of high pressure to a place of low pressure. This difference is what we call potential difference, and it is the only reason electricity ever flows. The ground beneath us, the soil and the roots and the stones, is at what we call zero potential. It is the baseline. The wire the bird is sitting on, however, is at a much higher potential, perhaps tens of thousands of volts. But because the bird is only touching that one wire, and its feet are not touching the ground or any other object, there is no path for the electricity to take. There is no downhill for the energy to roll. Imagine a bird floating on a very high tide, miles out at sea. The water might be hundreds of feet deep, and the surface might be elevated far above the ocean floor. But as long as the bird is just bobbing on the surface, it doesn't feel the depth or the pressure of the water beneath it. It is simply moving with the tide. In the same way, when a bird lands on a high-voltage wire, its entire body instantly reaches the same electrical potential as the wire. Its feathers, its beak, and its tiny claws all rise to that same high pressure. Because the bird and the wire are at the exact same level of electrical height, the electricity has no reason to flow through the bird. It simply flows past, continuing its journey along the metal path. The bird is, for a moment, part of the circuit. It is a passenger on a high-energy journey, yet it feels nothing but the cool night air. If that bird were to stretch out a long wing and touch a different wire, one with a different voltage, or perhaps a metal support beam connected to the earth, the situation would change. The electricity would suddenly see a shortcut, a way to move from high pressure to low pressure. It would rush through the bird to reach that lower state. But as long as the bird remains perched on its single silver thread, it is cradled in a state of perfect electrical balance. It is a peaceful image to hold in your mind, the bird, sleeping or resting, completely surrounded by a force that could power a city, yet remaining entirely untouched by it. It is safe because it is in harmony with the wire. It has become part of the high-voltage cloud that exists in that space. This cloud is more than just a metaphor. It leads us to one of the most profound and misunderstood truths in the world of science. We often imagine electricity as something trapped strictly inside the metal of a wire, like water flowing through a garden hose. We think of the copper or aluminum as the container, and the energy as the liquid inside. But in the quiet, invisible world of fields and forces, the truth is much more mysterious. The energy we use to light our homes and charge our phones doesn't actually travel inside the metal of the wire.
It isn't a stream of particles bumping through the center of the cable. Instead, the real power, the actual energy that does the work, exists in the space around the wire. It lives in an invisible electromagnetic field, a shimmering envelope of energy that follows the wire like a ghost. The wire is not the pipe. It is more like a guide or a track, showing the energy where to go, while the energy itself travels in the air, the insulation, and the void surrounding the metal. As you lie there, drifting closer to sleep, try to visualize this. Every wire in your home, every power line over your street, is surrounded by a soft, invisible glow of potential. It is a world of fields, overlapping and interacting in a silent, beautiful dance. We are surrounded by these invisible clouds of energy, working quietly to keep our world turning while we rest. It feels strange to think about, doesn't it? We spend our lives looking at wires and cables, thinking of them as the containers for electricity. We imagine the power is tucked away safely inside the copper, shielded by the plastic coating. But if you could see the world through the eyes of a physicist, you would see something entirely different. To a physicist, the metal is almost like a ghost, and the energy is a vibrant, invisible wind blowing alongside it. This is perhaps the most common thing people get wrong about how our world is powered. We are often taught in school that electrons flow through a circuit, and we naturally assume that the energy flows with them, tucked deep inside the wire. But while the electrons do move, very slowly as we've discussed, they aren't the energy itself. They are merely the anchors that allow the electromagnetic fields to exist. The electrons are the dancers, but the music, the energy, is in the air all around them. Imagine a train track stretching across a vast, dark plain. The tracks are the wires. They provide the path, the structure, and the direction. But the cargo, the actual energy,
isn't inside the rails. It's like a massive, invisible wave that follows the tracks, hovering just above and around them. This wave is made of two parts, an electric field and a magnetic field. When these two fields meet and interact around a wire, they create a flow of energy that moves in a very specific direction. Scientists have a beautiful name for this direction of energy flow. They call it the Poynting Vector. It is named after a physicist, John Henry Poynting, but it is a wonderful coincidence of language because this vector literally points the way the energy is going. If you were to look at a simple lamp cord in your room, the Poynting Vector would be an invisible arrow pointing from the wall outlet toward the light bulb. But importantly, that arrow lives in the space between and around the wires, not inside the copper itself. Think of the insulation on your phone's charging cable.
We often think of it as a barrier to keep the electricity in, like the walls of a pipe. But in reality, that insulation is where much of the energy is actually traveling. The energy is moving through the plastic, moving through the air, and surging toward your device in the space immediately surrounding the metal. The wire is simply the shepherd, calling the energy forward and giving it a track to follow. As you lie there perfectly still, you might begin to realize how much is happening in the quiet spaces of your room. The air around your lamp, the space inside your walls, it isn't just empty. It is filled with these silent, invisible vectors, all pointing toward the things that need power. It is a hidden architecture of energy, a web of fields that supports our modern life without ever making a sound or a movement that we can see. The energy is all around the wires, cradling them, moving in a silent, steady stream toward its destination.
If you picture the wire as a long silver guide rail, you can see that it doesn't actually carry the load inside its own body. Instead, the energy is like a phantom train hovering just above the track, moving with incredible speed and purpose. The wire is the anchor, the reference point that tells the energy where to go. Without the wire, the energy would dissipate in every direction, like a mist or a fading echo. But with the wire, it is focused, channeled, and brought exactly where we need it to be. The metal provides the electrons to hold the field in place, but the space around the metal provides the room for the energy to run. This is why the insulation around a wire, that familiar plastic or rubber coating, is so much more than just a safety feature to keep us from getting a shock. It is actually a vital part of the energy's path. We often think of insulation as a wall, something meant to stop things. But in the world of physics, it is a medium. Different materials for insulation are chosen because of how they allow these electromagnetic fields to pass through them and stay contained. In a way, the insulation is the specific atmosphere that the energy train breathes. It helps manage the shape and the strength of the fields, ensuring the energy stays bundled close to the wire and doesn't leak away or interfere with other nearby circuits. When you touch a cool plastic cord, you are touching the very layer where the energy is performing its silent work. Take a slow, deep breath now. As you exhale, let your shoulders sink a little deeper into the mattress. Imagine the quiet room around you. Even in the silence and the darkness, there is this gentle, invisible activity. Your lamp cord, the wiring hidden behind the drywall, the charger near your headboard, they are all surrounded by these soft, pulsing fields of energy. They don't make a sound,
They don't vibrate.
They simply exist in the space, a hidden layer of the world that supports your comfort and your safety. It is a peaceful GK thought, knowing that the energy is handled so carefully, guided by simple threads of metal and kept in place by humble layers of plastic. You are surrounded by a web of organized, quiet power that EGK GDK. There is something even more profound about these fields that live outside the wire. They aren't just a single force. GDK, see, whenever electricity flows, it doesn't GDK an electric field. It also GDK its inseparable twin, magnetism. You cannot have one without the other. As the energy travels through the space around the wire, it reaches out and tugs ever so gently on the very fabric of the world, creating a magnetic pull that circles the wire like an invisible, protective halo. This connection, this perfect marriage of electricity and magnetism, is the foundation for almost everything in our modern world. It is the secret behind how we turn motion into light, and how we turn silence into power. These two forces are so tightly linked that they are often spoken of as one single, beautiful entity. One creates the other, and the other sustains the first in a cycle that never truly ends. It was once thought that electricity and magnetism were two entirely separate forces, like two distant stars that had nothing to do with one another. But we now know they are simply two different expressions of the same fundamental truth. We call it electromagnetism, and it is perhaps the most elegant partnership in all of physics. They are, in a very real sense, two sides of the same coin. Think of a simple piece of paper. One side is the electric field, and the flip side is the magnetic field. You cannot have the paper without both sides existing at the same time. This realization changed everything about how we understand the universe. It means that wherever there is an electrical charge in motion, a magnetic field is born, wrapping around it like a soft, invisible blanket. Imagine a simple copper wire. When it sits still on a table, disconnected and cold, it is just a piece of metal. But the moment you allow a current to flow through it, the space around that wire fundamentally changes. If you were to place a tiny compass near that wire, the needle would twitch and turn, sensing a new magnetic presence that wasn't there before. This happens because those moving electrons, those tiny, slow-moving particles we've been visualizing, naturally generate a magnetic field as they drift. It is as if the electricity is singing a low, magnetic note that the rest of the world can hear. This is the secret behind how we make electromagnets. By coiling a wire over and over, we can concentrate that quiet magnetic song into a force strong enough to lift heavy machinery or power the tiny, precise motors in your household appliances. It is a controlled, predictable kind of magic that allows us to turn an invisible flow of energy into a physical pull. But the most beautiful part of this partnership is that it works perfectly in reverse. Just as moving electricity creates a magnetic field, a moving magnetic field can create electricity. This is a principle known as induction, and it is one of the most important discoveries in human history. If you take a simple magnet and move it back and forth near a loop of wire, you are essentially pushing the electrons inside that wire with an invisible magnetic hand. You don't even have to touch the wire. The magnetic field reaches out through the air, through the vacuum, and through the silence, gently nudging those electrons into motion. It is a delicate, invisible conversation between the magnet and the metal. Imagine a mirror. When you move, your reflection moves with you, perfectly synchronized. Electricity and magnetism are like that reflection, They are so intertwined that a change in one ripples through the other instantly. This harmony is what allows energy to travel across the vast distances of space as light, which is itself an electromagnetic wave, a shimmering pulse of electric and magnetic fields leaping over one another in a cosmic game of leapfrog. But here on Earth, in the quiet of your room, we use this harmony for something much more grounded. We use it to bridge the gap between the physical world of motion and the invisible world of flowing charge. By understanding that a magnet in motion is essentially a fountain of potential electricity, we unlocked a way to harvest energy from the world around us.
This reciprocal relationship, this if you move, I move dance, is the very heartbeat of our civilization. It is the secret to how we generate almost all the power we use to light our cities and warm our homes. We found that if we can just keep something moving, if we can keep a magnet spinning or a wire dancing near a magnetic field, we can create a continuous, reliable flow of energy. This discovery turned the world from a place of flickering candles and manual labor into a world of constant, effortless light. It took the physical effort of motion and translated it into the silent, invisible language of the electron. As you lie there, perfectly still, it is peaceful to think that somewhere, perhaps many miles away, something is moving with steady, rhythmic precision to keep your world comfortable. This simple exchange between a magnet and a wire is the silent engine of the modern age, a cycle of motion and energy that hums along while the rest of the world sleeps.
And nearly all of that movement, across the entire planet, begins with one very simple mechanical action. That mechanical action, at its heart, is surprisingly simple. Almost all the electricity that powers our modern world, from the streetlights outside your window to the subtle hum of your refrigerator, is created by the act of spinning a wheel. In the world of engineering, we call this wheel a turbine. It is essentially a sophisticated fan designed to catch the movement of a fluid or a gas and turn that movement into rotational energy. Whether it is a massive structure at the base of a dam or a sleek, white blade standing in a windy field, the goal is always the same: to keep something turning. When you think of the sheer variety of ways we generate power, it can seem complex, but they are mostly just different ways of finding a pusher for that wheel. In a hydroelectric plant, it is the heavy, cool weight of falling water, pulled by gravity, that rushes through the turbine blades. In a wind farm, it is the breath of the earth itself, the moving atmosphere, that coaxes the blades into a slow, graceful circle. And in most other power plants, whether they use coal, natural gas, or the quiet, intense heat of nuclear fission, the process involves boiling water to create steam. That steam, under immense pressure, wants to expand and escape. As it rushes out, it is directed through the blades of a turbine, spinning it with incredible speed and force. This is where the mechanical world meets the electrical world. The spinning turbine is connected to a long metal shaft, and on the other end of that shaft is a massive magnet surrounded by coils of copper wire. As the turbine spins, the magnet spins with it, hundreds or even thousands of times per minute. This creates that constantly changing magnetic field we spoke of earlier, the invisible hand that reaches out and nudges the electrons in the wire into motion. It is a profound transformation. The physical, noisy, high-pressure world of rushing water or scalding steam is traded for the silent, weightless flow of charge. The kinetic energy of a moving river or a gust of wind is distilled down into the quiet pulse of electricity that eventually finds its way to your home.
It is a rhythmic, steady process that happens far away, often in isolated valleys or out on the open plains, while you rest in the stillness of your room. There is something deeply comforting about this cycle, the idea that the natural movements of the planet, the flowing of water and the shifting of air, are being captured and converted into the very energy that keeps us safe and warm. It is a mechanical process turned into an invisible one, a bridge between the tangible world we can touch and the subatomic world we can only measure. For over a century, this has been the foundation of our civilization. The spinning wheel, the dancing magnet, and the flowing electron. It seems almost universal, this requirement for motion and physical turning to generate power. Yet, as we look toward the future, we find there is one beautiful, quiet exception to this rule of spinning wheels. A way to harvest energy that requires no movement at all, standing perfectly still under the open sky. This exception is found in the soft, dark surfaces of solar panels, resting quietly under the open sky. While almost every other form of large-scale power generation relies on the physical turning of a wheel, solar energy is a silent, solid-state process. There are no massive magnets spinning, no steam whistling through pipes, and no gears grinding against one another. It is a direct conversation between light and matter, a phenomenon known as the photoelectric effect. To understand how this works, we have to look very closely at the material inside the panel, which is most often silicon. Silicon is a semiconductor, a material that sits in a delicate balance. It isn't quite a conductor like copper, but it isn't a total insulator like glass. In its natural state, the electrons in the silicon are held relatively tightly in place. But when a particle of light, called a photon, travels all the way from the sun and strikes the surface of the panel, it carries a specific packet of energy. When that photon hits an atom of silicon, it's like a gentle but firm knock on a door. It transfers its energy to an electron, giving it just enough of a kick to break free from its bond. Once these electrons are knocked loose, they are guided by an internal electrical field within the solar cell, which encourages them to move in a single direction. This movement, this steady stream of liberated electrons, is exactly what electricity is. It is a beautiful, elegant transformation. The panel doesn't make energy out of nothing. It simply catches the energy arriving from the sun and translates it directly into the movement of charge. There is no middleman, no mechanical motion required. Take a moment now to breathe deeply and imagine a vast, quiet field filled with these panels. The sun is high and warm, and the air is still. There is no sound here but the faint rustle of grass in a light breeze. While the world around them might be buzzing with activity, the panels themselves sit in perfect, meditative stillness. They are drinking in the light, and deep within their crystalline structures, billions of tiny electrons are being nudged into motion, flowing silently through silver ribbons and out into the world. It is a harvest of light, as quiet as the growth of a leaf. As we think about these different ways of gathering power, from the warmth of the sun, the rush of a river, or the heat of the earth, we often hear people use terms like clean energy or green power. This is a helpful way for us to talk about where our energy comes from and how it affects our planet. However, it sometimes leads to a common misconception: the idea that the electricity itself is somehow different depending on its source. We might imagine that solar electricity is somehow lighter or cleaner than the electricity coming from a coal-fired plant. In reality, once those electrons begin their journey through the wires, they lose all memory of how they were set in motion. To a light bulb, a computer, or the heater warming your room, an electron is simply an electron. There is no such thing as dirty electricity or clean electricity once it reaches the copper in your walls. Whether an electron was nudged by a photon of sunlight or pushed by a massive steam turbine, it carries the same charge and behaves in the exact same way. The electricity in our world is a single, unified force, a vast and invisible ocean that we all share.
As we move forward, we will look at how all these different sources, the sun, the wind, and the heat, pour their energy into one singular, incredibly complex system that spans entire continents. Think of a single electron. It is one of the most fundamental building blocks of our universe, a tiny point of negative charge that exists everywhere. If you were to take an electron that had been set in motion by a massive, humming coal-fired power plant in a distant valley and place it side by side with an electron liberated by a silent solar panel on a suburban rooftop, you would find that they are absolutely, perfectly identical. In the realm of physics, electrons are what we call indistinguishable particles. They carry no signature of their origin. They have no memory of the fuel that pushed them or the light that nudged them into the circuit. It is a quiet, leveling truth of physics. Once electricity enters the copper wires of the electrical grid, it becomes a single, unified resource. You might imagine it like a vast, communal reservoir of water.
Different streams might feed into that reservoir, some from mountain springs, some from deep underground wells, some from captured rainfall. But once those streams merge into the deep, still body of the lake, the water is simply water. When you turn on your tap, you aren't receiving rainwater or well water specifically. You are receiving the collective gift of all those sources combined. The electricity currently flowing through your home, perhaps powering the very device you are listening to, is a beautiful, invisible mixture of everything that has been fed into the system. It is the breath of the wind from a turbine hundreds of miles away, the heat of the earth from a geothermal vent, and the ancient energy of the sun captured by a field of blue glass. All of these different forces are translated into the exact same language, the movement of identical electrons.
This means that, in a very real sense, we are all connected by a shared current.
The energy that lights a hospital across the country is the same energy that warms your tea or glows softly in your bedside lamp. There is something deeply peaceful about this lack of distinction. It reminds us that, at the most fundamental level, the laws of nature are consistent and unbiased. An electron doesn't care if it was green or brown at its moment of creation. It simply follows the path of least resistance, carrying its tiny portion of energy to wherever it is needed. This uniformity is what allows our modern world to function. Every appliance, every motor, and every light bulb is designed to work with this universal, anonymous flow of charge. But managing this vast, anonymous flow is a task of staggering complexity. Because electricity cannot be easily stored on a massive scale, every single electron that is used in this very moment must be generated
in this very moment.
If 1,000,000 people turn on their lights at the same time, the system must instantly respond by pushing 1,000,000 more electrons into the wires. This delicate, constant balancing act happens within a structure so large and so intricate that it is often called the most complex machine ever built by human hands. As we settle deeper into our rest, we can begin to visualize this enormous, invisible web, the electrical grid, stretching out across the landscape, connecting every home, every city, and every person in a silent, synchronized dance of energy. It is a system that never sleeps, quietly ensuring that the balance is kept, even as the world around it slows down for the night. Visualize for a moment the sheer scale of this system. We often think of machines as objects we can see in their entirety, a car, a watch, or perhaps a large airplane. But the electrical grid is a machine so vast that no one person can see more than a tiny fraction of it at once. It is a singular, interconnected entity that spans entire continents, crossing mountains, deserts, and forests. It is composed of millions of miles of high-voltage lines, thousands of power plants, and countless transformers, all working in perfect synchronicity. In the world of engineering, it is widely considered the largest and most complex machine ever constructed by human hands. What makes this machine so remarkable isn't just its size, but its responsiveness. Unlike a reservoir of water that sits still until you open a valve, the electrical grid must be alive and moving at all times. Because electricity travels at nearly the speed of light, and large-scale storage is still a developing technology, the grid operates on a principle of perfect, instantaneous balance. Every single watt of power being used right now by your refrigerator, by a street lamp in a distant city, by the device in your hand, must be generated at the exact same microsecond it is consumed. Imagine a giant, delicate scale. On one side, we have the demand, the billions of devices and lights across the country. On the other side, we have the supply, the spinning turbines of dams, wind farms, and power stations. To keep the system stable, these two sides must remain in a state of near perfect equilibrium every second of every day. If the demand suddenly increases, perhaps as the sun sets and millions of people reach for their light switches, the supply must increase to meet it immediately. Operators and automated systems watch the pulse of the grid, a steady hum known as frequency, to ensure it doesn't waver. This pulse is the heartbeat of our modern world. In North America, it beats at 60 cycles per second. In much of the rest of the world, it is 50. As long as that heartbeat remains steady, the machine is healthy. It is a silent, constant effort, a feat of coordination that happens while we sleep, while we work, and while we dream. It is a testament to human ingenuity that we have created a system that can sense a single light bulb turning on hundreds of miles away and respond by nudging a turbine just a fraction of a degree faster. But maintaining this balance is a high-wire act of physics. When the demand becomes too heavy for the GDK, or if a sudden surge of energy enters the system unexpectedly, the balance begins to tip. The heartbeat of the GDK might slow down or speed up, straining the very metal and magnets that GDK really. In these moments, the machine must protect itself. Just as your own body has reflexes to protect you from harm, the grid has its own set of survival instincts. When the balance fails,
the consequences are immediate, leading us into the quiet, sudden stillness that occurs when the giant machine decides GDK something much worse.
When we find ourselves sitting in the sudden velvety darkness of a power outage, our first thought is often that the world has simply run out of energy. It feels like a void, a literal blackout, where the supply has dried up like a well in a drought. But in the vast majority of cases, a blackout is not a sign that electricity has vanished. Instead, it is a sign that the grid is doing exactly what it was designed to do. It is protecting itself. Imagine the massive copper wires and heavy transformers that make up our electrical veins. When the demand for power becomes too high, or when a storm knocks a tree onto a line, the flow of electricity can surge to dangerous levels. As we've learned, electricity generates heat. If too much current flows through a wire or a transformer, that heat can become so intense that the metal begins to soften, the insulation begins to char, and the very heart of the grid risks melting into a useless heap of slag. To prevent this catastrophic damage, the system is filled with incredibly sensitive reflexes called circuit breakers and relays. When these sensors detect a surge that could damage the infrastructure, they trip. They physically snap open the circuit, cutting off the flow of energy in a fraction of a second. This is the moment the lights go out. It is a controlled, intentional pause. The grid is essentially saying, "I need to stop now so that I can work again later." It is a sacrifice of the present moment of convenience to ensure the long-term survival of the machine. It is much easier to reset a switch than it is to rebuild a melted power station. Take a slow, deep breath and imagine that transition into the quiet. There is a unique, heavy silence that follows a power outage. The low-frequency hum of the refrigerator, a sound you likely didn't even realize you were hearing, suddenly vanishes. The tiny, high-pitched whir of electronics fades away. In this forced stillness, the world feels smaller, more intimate. You are no longer connected to the giant pulsing machine for a few moments. You are just here, in the soft shadows, perhaps seeing the stars a little more clearly through the window if the streetlights have gone dark too. It is a reminder of how much invisible activity surrounds us every second, and how deeply we have integrated this silent force into our lives. But even when the lights are on, and we think we have turned off our devices, the story of electricity doesn't quite stop. There is a strange, persistent mystery in our homes, a quiet, hidden consumption that happens in the shadows of our living rooms and kitchens. Even when a television screen is dark or a computer is asleep, they are often still drinking tiny sips of energy from the wall. This is a phenomenon that engineers and scientists sometimes call vampire power. It is a reminder that in our modern world, the flow of energy is rarely ever truly at zero, even when we are resting. Imagine the quietest corner of your living room at midnight. The sun has long since set, the house is still, and you have clicked the off button on the television remote. You might assume that the flow of electricity to that device has simply ceased, like water being shut off by a faucet. But if you look closely in the dark, you might see a tiny pinprick glow, a single red or blue LED light staring back at you. This small light is a sign of a much larger, invisible phenomenon. Even when we believe our appliances are sleeping, they are often still drinking tiny, persistent sips of energy from the wall. Scientists and engineers have a name for this: standby power. More colloquially, and perhaps a bit more evocatively, it is known as
vampire power, or vampire loads.
Take a soft, slow breath and consider the nature of this quiet consumption. It is not a malfunction or a leak in the traditional sense. It is a design choice built into the very fabric of our modern convenience. For a television to respond instantly to the press of a button on your remote, a small part of its internal circuitry must stay awake. It is like a tiny electronic ear, always listening for that specific infrared signal to tell it to wake up. To do this, it needs a constant, albeit very small, trickle of electrons. The same is true for your microwave or your oven. That glowing digital clock on the front requires a dedicated path of energy to keep time, while the rest of the appliance remains dormant. In every room of a modern home, these vampire devices are at work. Your internet router, your smart speakers, your computer in sleep mode, and even the bricks or transformers on your charging cables are all part of this silent network. If you have ever touched one of those plastic blocks plugged into the wall and found it to be slightly warm to the touch, even when it wasn't charging anything, you have felt vampire power in action. That warmth is the result of electricity moving through the transformer, being stepped down in voltage, and a small portion of it escaping as heat, even if there is no phone or laptop on the other end to receive the charge. While a single device might only draw a watt or two in this state, hardly enough to notice, the cumulative effect across an entire house and then across an entire city is immense. It is as if millions of tiny, invisible threads are constantly pulling at the great grid, ensuring that our world is always ready to spring into action at a moment's notice. It creates a sort of electrical background noise, a baseline hum of activity that never truly goes to zero. As you lie there, nestled in the comfort of your bed, you might think about how these devices are all tethered to the wall by their cords, physically bound to the copper veins of the house. We have become so used to these wires, the tangled nests behind the desk, the cables snaking across the floor, that we almost don't see them anymore. They are the physical bridges that carry the energy to our fingertips. But the story of how we move this energy is beginning to change. We are starting to find ways to bridge that final gap, to let the energy leap across the empty air without the need for a metal tether at all. This transition from the physical cord to the invisible field brings us to a concept that feels like science fiction, yet is rooted in a discovery made long before the first light bulb ever flickered to life. It is a common thought that wireless power is a marvel of the 21st century, a futuristic dream finally realized by the sleek gadgets we carry in our pockets. When you place your smartphone onto a charging pad and see the battery icon begin to glow, it feels like a quiet kind of magic, a clean break from the tangled history of copper and cord. But this magic is actually a very old friend. The principle that allows energy to jump across a gap without a physical wire was discovered nearly 200 years ago, long before the first computer or even the first reliable light bulb. If you look at an electric toothbrush sitting on its charging base, you will notice something interesting. There are no metal prongs, no exposed wires, and no plugs connecting the brush to the base. It is a solid piece of plastic resting on another solid piece of plastic. This is inductive charging, and it relies on a discovery made in the 1830s called electromagnetic induction. It is one of the most elegant dances in all of physics, a silent conversation between two objects that never truly touch. Inside that charging base, tucked away beneath the plastic, there is a small coil of copper wire. When you plug the base into the wall, electricity begins to flow through that coil. As we have learned, moving electricity creates a magnetic field. But because the electricity from your wall is alternating, switching directions many times every second, the magnetic field it creates is also constantly changing. It expands and contracts, pulsing like a slow, invisible heartbeat. When you set your device down, a second coil of wire inside the device enters that pulsing magnetic field. As the magnetic field washes over this second coil, it gently pushes the electrons inside it, coaxing them to move. This movement is a new electrical current, born from nothing but a magnetic shadow. The energy has successfully leaped from one coil to the other, crossing the plastic and the air, without a single electron ever having to leave its original home. It is a peaceful image to hold in your mind as you drift toward sleep. Two coils of wire, separated by a small space, yet perfectly in tune with one another. One whispers and the other hears. One moves and the other follows. This invisible bridge is what allows us to charge our devices without the clutter of cables. And it is what keeps us safe when we use electronic devices in the bathroom, where water and electricity must be kept strictly apart. But as you think about this invisible connection, you might wonder why we don't use it for everything. If we can send power across a small gap, why do we still need those thousands of miles of copper wire stretching across the landscape? Why do we still have to plug our lamps and our heaters into the wall? The reason we haven't yet cut all the cords in our lives comes down to a fundamental challenge of physics. While the air is a wonderful medium for light and sound, it is a very difficult path for energy to travel without getting lost along the way. To understand why our world remains tethered by wires, we have to look at what happens to that energy when it tries to travel further than a few inches through the empty air. The dream of a world without wires is a beautiful one. A landscape free of poles and hanging cables, where every device simply draws the power it needs from the air around it. But as we move from the tiny gap of a toothbrush charger to the vast distances of a living room or a city street, we run into a stubborn reality of physics. When energy is sent through the air without a physical guide like a copper wire, it begins to scatter. It behaves less like a focused beam and more like the light from a candle, spreading out in every direction at once. By the time that energy reaches its destination, only a tiny, faint fraction of it remains.
The rest isn't truly gone, but it has changed its form. It has become heat. Every time energy moves from one place to another, there is a kind of tax paid to the universe. In a well-insulated wire, that tax is very small, a minor loss that we can easily manage. But in the open air, the tax is immense. Most of the electricity we would try to beam across a room would simply vibrate the molecules of nitrogen and oxygen in the air, warming them up ever so slightly. If we tried to power a whole city this way, the air itself would become uncomfortably hot long before the lights in our homes even began to glow. This is why, for now, we rely on the quiet, hidden network of wires to keep our energy contained and efficient. We use the wires to make sure the energy goes exactly where we want it, without leaking away into the atmosphere as unwanted warmth. As you lie there, perhaps you can feel the subtle warmth of your own environment. Take a slow, deep breath and imagine the soft, steady heat of a small ceramic heater placed across the room on a cold winter evening. Visualize the thin wires inside that heater beginning to glow a soft, dim orange. In this specific case, the waste of electricity, the heat it creates through resistance, is exactly what we want. We aren't trying to move a signal or turn a motor. We are simply asking the electrons to struggle through a material that resists them. As they push through, they create friction on a microscopic scale, and that friction radiates outward as a comforting wave of warmth. There is something deeply soothing about that dry, golden heat. It fills the room slowly, rising toward the ceiling and wrapping around you like an invisible blanket. In the stillness of the night, that warmth is a reminder of how energy is always shifting, always looking for a way to express itself.
We often think of heat and light as two different things, but in the world of physics, they are often two sides of the same story. When something becomes hot enough, it begins to speak to us in a different way. It begins to shine. This relationship between the warmth we feel and the light we see has shaped the way we have illuminated our world for over 100 years, starting with a simple glowing thread of wire held inside a quiet glass jar. The classic pear-shaped bulb that has come to represent a bright idea is, in reality, a bit of a misnomer. If we were to judge it strictly by its output, an incandescent light bulb is actually a much better heater than it is a source of light. When you flip the switch and that thin tungsten filament begins to shimmer with a warm golden glow, it is performing a feat of incredible physical endurance. The electricity is being forced through a wire so thin and so resistant that the metal begins to vibrate with intense energy. It reaches temperatures of thousands of degrees, becoming so agitated that it starts to shed photons, the tiny particles of light that allow us to see in the dark. HGK's process is incredibly taxing and surprisingly inefficient. Roughly 90% of the energy you send into that bulb never actually GDK. Instead, it radiates away as invisible infrared heat, warming the GDK, the soft air around the lamp, and eventually the entire room. Only a tiny 10% fraction of that energy is left over to push back the GDK of the night. In a very real sense, an old-fashioned light bulb is essentially a small glowing furnace that happens to leak a little bit of illumination as a byproduct. You might remember the caution of childhood, being told never to touch a bulb that had been on for a while, because that glow plug heat was intense GDK. It was a beautiful, warm light, but it was a heavy consumer of power, demanding a great deal of energy just to keep that tiny thread of metal at the brink of melting. For over a century, this was simply the price we paid for the convenience of having artificial suns in our homes. We accepted the heat because we needed the light. But in recent years, a quiet and elegant revolution has taken place inside our lamps and fixtures. The transition to LEDs, light-emitting diodes, has fundamentally changed our relationship with electrical energy and how we use it to see. Unlike the old incandescent bulbs, an LED doesn't rely on scorching a piece of metal into submission. It uses a sophisticated process called electroluminescence, where electrons move through a specially designed semiconductor material. As they move, they drop into little holes in the material's atomic structure, and in that moment of falling, they release their excess energy directly as light. Because there is no need for extreme friction or extreme heat.
Almost all the electricity is converted into the very thing we want: visibility. This is why LEDs are so revolutionary. They are cool to the touch, even after they have been shining for hours. They represent a much more direct and peaceful translation of energy, allowing us to light our world without the heavy, invisible tax of wasted warmth. It is a cleaner, more focused way for energy to move, silent, efficient, and gentle on the environment. This shift from heat to light is a calming reminder of how versatile electricity truly is. We have spent so much of our history using current to create warmth, to cook our food, to heat our water, and to light our paths through the friction of resistance. But there is a hidden, beautiful symmetry in the laws of physics. If electricity can be used to generate intense heat, it stands to reason that it might also be used to do the exact opposite.
Just as energy can be pushed into a material to make it vibrate and grow hot, it can also be carefully manipulated to draw heat away from a surface, creating a pocket of stillness and cold. This is one of the most counterintuitive wonders of the electrical world: the ability to use a moving current not just to burn, but to chill. As you settle deeper into the cool comfort of your sheets, consider how this same invisible force can move heat from one place to another, creating a quiet balance in the temperature of our world. As we think about the warmth of those old light bulbs, it is fascinating to realize that electricity can do the exact opposite. It can create a profound, deep cold without a single moving part. This is achieved through what scientists call the Peltier effect, a phenomenon that feels almost like a quiet magic when you first encounter it. Imagine taking two different types of conductive materials, such as two different metals or semiconductors, and joining them together to form a circuit. When a gentle, direct electrical current is whispered through this junction, the electrons don't just move along the path, they carry thermal energy with them. On one side of this tiny bridge, the material begins to lose its heat, becoming colder and colder as the energy is literally pulled away. Meanwhile, the other side grows warm as it receives that displaced heat. It is a solid-state heat pump, operating in total, blissful silence. Unlike a refrigerator in a kitchen, which uses a loud compressor and flowing liquids to keep things cool, a Peltier device has no hum, no vibration, and no mechanical parts to wear down. You might find this technology in a small, quiet, bedside cooler, or even in the sophisticated instruments of a space probe, where the vibration of a traditional cooling fan would be too disruptive for delicate sensors. It is a reminder that electricity is a master of balance, capable of shifting energy from one place to another with nothing more than a steady, patient flow of charge. In this quiet exchange, we see the true, multifaceted nature of the electron. We have seen it crawl like a snail through copper wires, leap across the sky as lightning, and now we see it acting as a silent porter, carrying heat away to create a pocket of stillness and chill. This ability to manipulate the very temperature of our surroundings is a testament to how deeply we have learned to dance with this invisible force. But as we lie here in the stillness of the night, it is helpful to broaden our perspective even further, moving beyond the gadgets and the grids of our modern world. The electricity we use to charge a phone, light a room, or cool a drink is only a tiny, localized manifestation of a much grander reality. We often think of electricity as something we generate or turn on, as if it were a guest in our world that we invite in through a socket in the wall. But the truth is far more profound and perhaps more comforting. This force does not just exist within our wires and batteries. It is the very scaffolding of the cosmos. From the smallest atom to the most distant star, the electromagnetic force is the silent conductor of the universal orchestra. It is the glue of existence, a force so powerful and so pervasive that it shapes every moment of our lives, even when we are fast asleep and dreaming of distant places. As we move from the small scale of our homes to the vast scale of the universe, we begin to see that electricity is not just a tool, but the very reason we can exist at all.
As we widen our gaze from the small, silent cooling of a circuit to the vast expanse of the cosmos, we find that the electromagnetic force is not just a guest in our world, it is the very architecture of reality. We often live our lives thinking of electricity as a utility, something that arrives through a bill or a charging cable. But in the grander tapestry of the universe, it is one of the four fundamental forces that dictate how every single thing exists. Without it, the universe would have no structure, no light, and no life. It is the silent, invisible glue that holds the stars together and keeps the smallest grain of sand from drifting apart. Consider for a moment the bed where you are resting right now. It feels solid beneath you. It feels like a firm, physical barrier between you and the floor. But if we were to look through a microscope of incredible, impossible power, we would see a reality that is much more fluid and strange.
We would see that atoms, the building blocks of everything you see and touch, are mostly made of empty space. If an atom were the size of a vast football stadium, the nucleus, the center, would be no larger than a small marble sitting on the 50-yard line. The electrons would be like tiny gnats buzzing far away in the highest, most distant seats of the stands. Between that marble and those gnats, there is nothing but vast, open territory. By all rights, based on the sheer amount of empty space within us, we should be able to pass right through walls, or sink through the floor, or drift through our blankets like ghosts. But we don't. And the reason we stay exactly where we are is because of the incredible power of the electromagnetic force. As you lie there, gravity is doing its quiet, persistent work, pulling your body down toward the center of the earth. It is a heavy, comforting tug that settles you into your blankets.
But the reason you don't keep falling, the reason you stop right at the surface of your mattress, is because of electricity. The electrons that surround the atoms of your body carry a negative charge. Similarly, the electrons that surround the atoms of your bed also carry a negative charge. And as a fundamental rule of our universe, like charges repel one another with a force that is almost unimaginably strong. In a very real, physical sense, you are not actually touching your bed at all. At a microscopic level, there is a tiny, invisible gap between the atoms of your skin and the atoms of the fabric. You are hovering. You are resting on a microscopic, invisible cushion of electrical repulsion. This force is so powerful that it can counteract the gravity of the entire Earth, holding you up and keeping you safe. Every sensation of softness you feel, every bit of support from your pillow, is actually the result of trillions upon trillions of tiny electrical fields pushing back against your weight, creating the sensation of touch. It is a beautiful, quiet balance.
This same force is what allows your muscles to move, what allows your eyes to perceive the soft glow of a lamp, and what keeps the molecules of your very soul held together in a perfect, intricate pattern. You are a being of light and charge, resting on a foundation of pure energy. As you feel the weight of your limbs and the softness of your surroundings, you can take comfort in the fact that the entire universe is working in harmony to hold you exactly where you are. The fields are steady. The forces are in balance. The world outside may be vast and complex, but here, in the stillness of your room, the laws of physics are acting like a gentle, invisible cradle. You are supported by the fundamental constants of the cosmos, a quiet participant in the grand electrical dance of existence. And as you acknowledge this profound connection to the stars and the earth, you can feel your thoughts begin to drift, moving away from the how and the why, and simply settling into the peaceful is. The invisible fields around you are quiet, and the energy of the day is slowly ebbing away, leaving only the soft, rhythmic pulse of a world at rest. As we reach the end of our journey through the invisible world of electricity, take a moment to reflect on how far we've traveled tonight. We began at the very smallest scale, watching individual electrons drift through copper wires at the pace of a garden snail, yet carrying signals that move at the speed of light. We saw how their collective movement creates the powerful energy that lights our cities and powers our lives. We looked at the immense, interconnected machine of the global grid, the largest structure ever built, balancing supply and demand in a silent, perfect symphony across continents. From the crackle of a winter sweater to the majestic, upward-reaching streamers of a lightning bolt, we've explored the forces that shape our reality and keep our world in motion. Now, all of that vast energy and complexity feels very far away. The hum of the world has faded into the background, leaving only the stillness of your room. The power lines stretching across the moonlit fields are quiet and steady. The turbines in distant valleys are spinning with a rhythmic, mechanical grace, and the electromagnetic fields around you are in a state of perfect, peaceful balance. There is no tension here, no resistance, only the soft, steady flow of existence. You are part of this balance, a calm point in a world of energy. Even now, as you lie still and your breathing slows, your own internal electricity is undergoing a beautiful transformation. Your brain, that wonderful and complex biological circuit, is shifting its frequency. Throughout the day, your mind hummed with the quick, sharp electrical pulses of active thought, known as beta waves. But as you drift closer to the edge of sleep, those waves are lengthening and softening. They are becoming the slow, rolling pulses of alpha and theta waves, eventually giving way to the deep, heavy rhythm of delta waves. These are the electrical signatures of true rest, the gentle oscillations that allow your body to heal, your memories to settle, and your mind to dream. Your brain is essentially tuning itself to a lower, calmer station, preparing to enter the deep, restorative silence of the night. Everything is exactly as it should be. The fundamental forces of the universe are holding you safely, providing the invisible cushion that supports your weight. The electrons are at rest in their shells, and the fields of the earth are quiet and constant. You have traveled through the history of discovery, the mysteries of nature, and the science of the everyday. You have learned all you need to for today, and now the only thing left to do is let go. Let the weight of the day dissolve into the velvet dark, knowing that the world is being powered and protected by the very forces we've discussed. Take one last, slow, deep breath. Feel the coolness of the air as it enters and the warmth as it leaves. You are safe. You are supported. You are at peace. Thank you for spending this quiet time with me, exploring the hidden currents of our world. May your rest be as deep and steady as the earth beneath you. Sleep deeply, dream of soft light and starlight, and rest well. Good night.